In this unit on energy and work and machines, I'm going to be hitting you with a lot of formulas, and you're going to be able to have to use these formulas in order to, do what formulas do. They come up with answers to things you calculate, right? Work has a very specific meaning in physics. You can get paid for thinking, right? But most commonly, when we think about work, we think about doing stuff. And my example that I use in class about doing work is moving an object, like pushing furniture around. You can actually get paid for moving furniture, right? And this has a direct relationship to what the meaning of work is in terms of physics. In order for there to be work done, an object has to move. So for an object to move, there has to be a force pushing on it. And we determine the amount of work done by simply multiplying the amount of force times the distance that force is applied. And we measure work in joules. Joules, you remember from our study about energy, kinetic energy, potential energy. Energy is measured in joules also. So therefore, there must be a relationship between work and energy, and there is. And as we go through this, you'll see more explicitly how they're related. So as you've worked through this packet, you've had some things you've had to calculate in terms of work. You multiply the force times the distance, easy enough. And then there's this concept of power. P for power. P is like your paycheck, how much you get paid. So if I'm going to get paid for doing work, for pushing furniture around, you get paid more or less depending upon how good you are at the work that you do. Okay? So people who are better at doing the work get paid more than people who maybe are not so good. And that can be seen in the physics analogy here. The amount of work you do divided by the time that you accomplish that work. It's a rate of doing work. It's like your paycheck. You get paid at an hourly rate. You get paid $10 an hour. You get paid $20 an hour. So people who get paid $20 an hour, you would think are doing more work or at least better at it than people who are getting paid $10 an hour. So power, like horsepower in physics, is a rate of doing work. It's also, since work is related to energy, it's also how much energy is transferred from one place to another. So we can talk about, a lot of times when you think of power, you say, well, what is the power of, that we're using at the house, right? How much energy is being transferred from the electric company to your house. So that's another way to think about power. And we can think about efficiency. If we're supplying a machine with a certain amount of energy, do we get 100% of that energy transferred into the work done? Not usually. In an ideal case, we would. If we put 20 joules of energy into something, we would want to get 20 joules of work out of it. But that's not always the case because there are losses in the system and things like that. But ideally, this is what we shoot for. So when people are trying to do things like, well, electric cars are more efficient, that's what they're talking about. If we put 20 joules of energy in the car, then we want our car to do 20 joules of work moving our bodies, the object, down the road a certain distance, right? So this is the efficiency. So electric cars are more efficient than gasoline cars. That depends on how you calculate it, but these are the kinds of problems that people are solving involving work, power, and efficiency. I'm going to give you an example that was on the back page of your packet. On the back page of your handout, it talks about two conveyor belts. Conveyor belt A and conveyor belt B. You don't need to look at the description on the back page of your packet because that's what I'm doing. I'm presenting this information to you. But what I do want you to do is on the handout that I gave you where I reworked the table, I want you to fill that out as I go along. Okay? So we have conveyor belt A and conveyor belt B. A conveyor belt does exactly what it says. It conveys stuff down the road. You might have seen like pictures of factories where things are moving on belts. That's what this is supposed to be. Now these belts, they kind of look like tank tracks. They go roundy round, but there has to be some motor driving that conveyor belt. But as you can see, as the motor turns, that's going to turn this, that's going to turn the belt, and if something's sitting on the belt, then whatever's on the belt is going to move. Now, conveyor belt A moves this box 1 meter. Now, this box has a force associated with it. How, we're going to have to apply, this belt is applying a force to this object, a force of 10 newtons to move this box this distance. Conveyor belt B is moving this same box with the same force, but it's moving it 2 meters in the time that it takes this conveyor belt to move it 1 meter. So let me say that again. Conveyor belt A moves the box 1 meter in 3 seconds. Conveyor belt B moves this box 2 meters in 3 seconds. Now you can already begin to think about, well, which one's better, because you already have some intuitions about which one's going to be doing more work. Well, let's go ahead and calculate that. The work that we're getting out of this machine is the force that's being output times the distance of that it's being moved. The force that's being applied, we're given as 10 newtons, and the distance that the object is moved is 1 meter. So let's see. Multiplying 10 times 1 equals 10. Thank you very much. 10, a newton times a meter is a newton meter, but that's also known as a joule. So we are getting 10 joules of work out of this machine. So let's look at conveyor belt B. Yes, you're following along. I think I skipped the first line there, but you guys are smart. I'll come back to that in just a minute. The work we're getting out of the second machine, we're applying the same force of 10 newtons. That's our force out. The distance that it's moving, though, however, is 2 meters. So let's see. 2 meters times 10 newtons is 20 joules. 20 joules. Okay? So this machine, conveyor belt B, is doing 20 joules of work. Conveyor belt A is only doing 10 joules of work. Okay? Now, that may be good or bad. It depends on the rate that it's doing the work. So that's where we're going to calculate the power. So let's take the work. So to calculate the power, you need to divide the amount of work divided by the amount of time. So let's see, we're going to take 10 joules divided by the amount of time. Up there on the clock, that's 3 seconds. So 10 divided by 3 is 3.333. Now, power is measured in watts. Power is measured in watts. Erica, Mr. Watt was a guy, so we're going to capitalize the W for watts. Over here, the power is 20 joules divided by that same amount of time, 3 seconds, and the answer to that is 6.666 watts. Think of this, again, this power calculation like your pay. The power like the pay. Guess who gets paid $3 an hour compared to who gets paid $6 an hour? Why does conveyor belt B get more?
Because it moves a greater distance.
Yeah, it's moving the box twice as far in the same amount of time. So that person's going to get paid more, right? I don't know. Maybe that's not really a good analogy, but I think it works. For P, for power, for your paycheck. You can think about that. It's a rate of doing work. One more thing we have to calculate is the efficiency. And that's where we're going to get into how much energy do we put into this system. We're putting 20 joules of energy into each motor, and we're getting a certain amount of work out of it. So for this first machine, we're getting 10 joules of work out of it, and we're putting 20 joules into it. Joules divided by joules is nothing, and 10 divided by 20 is 0.5. Don't forget to multiply by 100 because we're calculating percent efficiency. And so conveyor belt A is 50% efficient. Conveyor belt B, we're going to get 20 joules of work out of it for every 20 joules of work we put into it. That's 100% efficient. There's not any machines that are really 100% efficient. But in this example, this allows us to compare two different conveyor belts that work at different rates.